Also, as a reminder, for more Microsoft Webcasts, you can visit microsoft.com/webcast. And again, I'd like to welcome everyone to today's Msdn webcast, Building a High-Performance Application Using the .NET Compact Framework. It's my pleasure to introduce today's presenter. We have Stephen Pratcher joining us today. Now, Stephen is a Senior Development Lead here at the Microsoft Corporation. And now, without any further delay, I'm going to turn the floor over to Stephen.
Hi, everyone. Thanks very much for tuning in to today's webcast on performance with the .NET Compact Framework. You know, performance in systems like .NET can be a bit tricky because of the various layers of indirection and abstraction that are built into the system. When you're programming with a native programming model, you have a pretty high degree of control over what's happening with your application as it's running. In .NET, we have a number of features that make it very easy to do all sorts of stuff. So things like the garbage collector for managing memory and the JIT compiler, a type system, reflection, and those sorts of things. Those are all wonderful productivity features, but these features can slow down your application if you're not aware of how they work. So one of my main goals today is to give you enough information about how the Compact Framework works internally so that you can make better diagnosis decisions when looking at performance issues. So the talk is grouped into two primary sections. At the beginning, we'll look at some of the low-level components of the Compact Framework to give you that in-depth knowledge that I was just referring to. I'll also show you a demo of the diagnostic tools suite that we have, and we'll step through a particular performance issue related to memory management so you can get a sense for the types of tools we provide and how you can use them to diagnose problems. Then in the second half of the session, I'll go through a number of tips and tricks for various areas of the framework that we've found over the last few years are most effective for writing high-performance applications. So let's start right in at a fairly low level of the system and start by talking about the JIT compiler. So as you're aware, .NET language compilers emit an independent language that then is compiled into native code as the application runs. So clearly there are two aspects to JIT performance that we need to be concerned with. The first is how long does it take the compiler to actually compile the code? And then the second is how good is the JITted code, or how quickly does that code run after it's emitted? So in terms of JIT time costs, there's really not a lot you can do to avoid these costs. Any time that we're about to call a method that has not been JITted yet, we'll go ahead and JIT that method, and then we keep the code around so that subsequent calls to that method are quick, no compilation is involved. But the key thing to remember in terms of JIT time costs with the Compact Framework is that we don't have the capability to persist code anywhere, and we do throw code away in order to conserve memory under certain situations. So because of that, we tend to do maybe more JITting than you would expect with a comparable application on the .NET framework, the desktop .NET framework. So because of that, our JIT compiler has been designed from the very beginning to generate code as quickly as possible, maybe at the expense of having the most optimal code come out the back end of the compiler. So our compiler is very good at taking one line of IL code and translating it quickly into one line of assembly code for whatever processor we're on. But we don't do a lot of optimizations. And again, that's because we need to regenerate code if we throw it away, and because there's no persisting of JITted code anywhere on the device. So even though I said that we don't do much optimization, it's interesting to look at a comparison between some performance numbers that come out of the code generated by the .NET Compact Framework JIT compiler and a native C compiler. One of my colleagues, Ryan Chapman, did an in-depth study of these performance comparisons, and this blog reference at the bottom of the screen here points you to all his findings. But it's interesting to see that in several cases, the performance of the C# or the VB code that comes out of our JIT compiler is fairly close to native code. In other cases, where it's clearly not. So I want to point out specifically the areas like the loops, the final row in the table here. You can see that native code optimized for this particular loop test was 0 milliseconds, and that literally was because of the optimizations done to hoist variables out of loops and flatten them and such things, such that code was actually removed from the system before it ran. So that's one example of where a native compiler will clearly outshine the work that we do in our JIT. And again, it's because the focus is on speed of compilation rather than necessarily on speed of the resulting code. But anyway, go ahead and read the blog article. It goes much more in depth about the particular tests that he ran, the numbers that he found, and the assembly code that was generated by each of the various compilers that he was comparing here. If you look at the runtime cost for calling methods in the .NET Compact framework, we find that just calling a regular instance method is about 2 to 3 times the cost of a native function call. So these numbers can help you kind of build up a cost model in your head, if you will, of the relative expense of a managed method call relative to a native method call. Virtual calls are a bit more expensive yet. That's for 2 reasons. Primarily, the cost for looking up the virtual method that we need to call. One of the techniques the Compact framework uses to reduce the amount of memory needed at runtime is that we don't build full virtual call tables for every class that we load. Instead, each time we're asked to call a virtual method, we look it up, we find it on the fly, and then we cache it for later. So the first call to a virtual method is going to be more expensive than subsequent calls. So that's one reason that the cost is a little higher than a regular instance call. The other reason that a virtual call can be a little more expensive is that it can never be inlined, obviously, because we have to dynamically figure out where to jump in order to execute the code, so we can't inline it. Towards the end of the presentation today, I'll spend a bit of time talking about the cost of interop, platform invoke, and COM calls. But in general, you can think about 5 times the cost of a managed instance call for doing pinvoke. And this is in a simple case where there isn't any complex marshalling to do. Also remember to watch for places that are, we think of as hidden method calls. I've seen people take very simple methods and turn them into properties, thinking that a property access is the same as a field access. Well, in fact, a property access is literally just an instance call, so it's the same cost as calling any other method. So moving things into properties doesn't save any time. The other thing to be a bit cautious of is the for each statement in C#. This is a very convenient way to iterate your way through collections, but if you look at the IL that's emitted by the compiler whenever you use for each, you'll notice that it generates virtual calls to the methods of IEnumerable. So if you're using for each a lot in large loops, loops where you're iterating many, many times, this can start to be a performance issue as well. So that's another case of a hidden method call. So just like most compilers, we do some simple optimizations. I don't want to say we don't do any. We do method inlining for very simple things. We won't inline anything that has much branching in it or any exceptions at all. I think we only inline if it's very small body of IL, like 16 bytes or something like that. but we do some. And then we do some string interning as well. So you can't really talk about performance in .NET and on devices in particular without talking about the garbage collector and automatic memory management. So the garbage collector is one of the great productivity features in .NET. It removes objects when you're no longer referencing them. It does a bunch of work on your behalf to make sure that your application performs well under low memory conditions on the device. But it is important to understand how it works in order to design your application to work very well. It's also important to know how to analyze when you're having issues related to memory management, and that's where the diagnostic tools come in that we'll look at in a few minutes. The garbage collector on the compact framework is pretty straightforward. It's not a multi-generational system like on the full .NET framework. We just maintain a single GC heap. Everything's in one area, so to speak, not in generations. And during a collection, we just traverse the object graph and mark all the objects that are still reachable from a GC root and then free the rest of them. So even after understanding how the collector works and going through and tuning your application so that all the managed memory accesses are used optimally, you still have to remember that there is some memory that can't be reclaimed by the garbage collector. So again, the GC heap is not the only heap that's going to be in your WinCE process. Any native memory that your application allocates by any calls to pinvoke or com, those certainly count. And then also, the .NET Compact Framework generates some runtime data structures as it's executing your application. These data structures represent primarily classes and methods, also things like app domains and assemblies, and just the various bookkeeping data that we need in order to load classes and compile methods and call methods. And these also are native allocations done by our runtime itself. So they as well can't be reclaimed by the GC. So again, just keep in mind the GC heap isn't the only memory heap in your process that's of interest when it comes to thinking about performance and how much memory you're using. So what triggers a garbage collection? The primary thing that causes a collection to happen is that 1 megabyte of objects have been allocated by your application. So as your application runs, it begins to allocate objects, and every time a megabyte of objects has been allocated, a collection kicks in. So a collection will kick in after 1 megabyte and maybe free a little bit. You'll allocate another megabyte. It'll collect again, free a little bit, and so on. We'll also trigger a collection when we fail to allocate some resource, such as memory or a window handle or any other sort of OS resource. And we do this with the idea to free up as many resources as we possibly can in the hopes that we can then try again to allocate the resource we were after, and this time we'll get it. Another case in which the collector fires is when you move an application to the background on your device. So, on Windows Mobile in particular, the model is often that you don't close applications when you exit them, so to speak. You are just moving them to the background, and then when you activate them again, they just come to the front. So when an application goes to the background, the Compact Framework will do a garbage collection. It'll free all of the objects that it can, and it'll return as much memory to the operating system as it can, so that the application that's coming to the foreground has more resources available to it. And the final thing that can cause a garbage collection is calls to gc.collect. And you've probably heard the endless spiel about why that's not such a good thing. So let's first talk about what happens during a garbage collection, and then I think that statement will make a little more sense. So the first thing that happens during a collection, and probably the most costly thing actually, is that all threads running in the process have to be rendezvoused at a point at which it's safe to do a collection. So there can't be any threads running that can manipulate the GC heap in any way while the collector is going through it. So time is spent waiting for all threads to get to a point where they can stop. Then we start at the top of the reference graph in the GC heap, and we find all objects that are still referenced, and we mark them. Then we go through, and for the unmarked objects, there are two cases. If an object does not have a finalizer, then the memory is freed right then. If the object does have a finalizer, then instead of freeing the object, we move it to a finalization queue to run the finalizer. Then, depending on the amount of fragmentation that we detect within the GC heap, we may compact the objects down so they're all moved closer together. And then if there are sections of the heap that we are no longer using, we'll return those to the operating system. So when the garbage collector allocates memory from the operating system, it allocates that memory in 64K blocks. So after a compaction, there may be some of those 64K blocks that are available, in which case those are candidates to return to the operating system. However, there's one more catch. We always keep around a 1 megabyte cache of these 64K segments, if you will. So we found over time that keeping that 1 megabyte cache allows us to perform much better on subsequent allocations than if we had to go right back to the operating system to get more memory back. So for example, say a garbage collection pulls the number of bytes of live objects down under 1 megabyte. Then the next time an allocation occurs, since we have this reserved block of memory, allocations are super fast. It's just simply a matter of moving a pointer down in the heap that corresponds to the object size. Whereas if we didn't keep that cache, we'd have to go back to the OS to get more memory, which is costly. So the only time that we'll free that 1 megabyte cache is either when we go to the background or under low memory or resource stress. So clearly the garbage collector only impacts you when it runs. I guess that's fairly obvious. There are, again, two primary metrics to consider when looking at GC performance. The first is how long it takes the collector to run, and then the second is how often the collector kicks in. So as we've seen, the time it takes the garbage collector to run is a function of the number of live objects or reachable objects that are in your heap. And again, that's because we're traversing the object graph, and every object that's still referenced simply takes more time to traverse through the graph. So the bigger the graph, the longer it takes to go through it. The time at which the garbage collector kicks in is primarily a function of the number of bytes of objects that you're creating. So again, after every 1 megabyte, the collector kicks in. So the more you allocate, the more the collector kicks in. And the memory management is another example of where there are features that you'll use as part of the .NET Compact framework that have side effects that can affect the performance of your application. So in particular, operations like string manipulations and the boxing of value types can have negative effects on performance by creating a lot of garbage on your behalf. And we'll look at some examples of that in a minute. So that leads to this thought of competing strategies for what's the best way to allocate objects in your application. What's the best strategy to reduce the impact that the garbage collector may have on your application? So one school of thought says, well, let's just allocate objects, maybe up front or as we need them, and then we'll just keep them around. That makes it a lot faster to use them in the future because we don't have to go back and allocate them again. However, the disadvantages to this approach are there's more memory pressure. The GC is going to run more often because more stuff has been allocated. It's also going to take the collector longer to run because you have kept objects alive for a longer period of time, so therefore they're likely to build up over time and result in a larger object graph. So then you think, well, let's just use short-lived objects. So the advantage here is there's less memory out of the heap being used at any given point in time. However, you are allocating a lot of objects, which hopefully in most cases is very quick, but if we trip over one of these 64K boundaries that I was referring to earlier, then we need to go back to the operating system to get more memory, which can slow you down. The other disadvantage is you may end up generating a lot more garbage. Maybe you're creating a large number of short-lived objects that just live for a very short amount of time and then are collected right away. So you're allocating and collecting and allocating and collecting. So there's more churn, so to speak, happening in the GC heap, and the collector is doing more work. So, not surprisingly, I hope, there's really no right answer to this question of these competing strategies. It's really best to try different approaches, use the diagnostic tools to see how the collector is being affected by your allocation strategy, and then kind of decide from there what the best approach is. Okay, so I mentioned that one of the causes of hidden garbage, so to speak, is this operation referred to as boxing. So as you likely know, the type system in .NET consists of two sorts of types or kinds of types. There are value types, which are stack-based types, and reference types, which live in the GC heap. And boxing occurs when you're casting a value type to a reference type. And that's costly for two reasons. The first is when these boxing operations occur, a new reference type needs to be allocated, so you're doing a memory allocation, and then all the data that was in the stack-based value type gets copied into the GC heap at the location where the allocation occurred. So it's kind of a two-phase cost to boxing. So this little code sample here shows an example. So here I have an array list of just an array list, and then I'm looping through my array list, creating new instances of this type called point. And then I'm calling ArrayList.add to add these new points to my array list. So on the call to add is when a boxing operation occurs. And to understand why this is true, you need to look at the definitions of both the type that we're adding to the array list and of the add method on ArrayList itself. So we can see that the point type is defined using the C# keyword struct, which is a value type, and that the add method to ArrayList takes an instance of the reference type object. So every time the value type point is passed to that method taking a reference type of object, this boxing operation occurs. Okay, so let me show you an example of how we can use the Compact Framework diagnostic tools to figure out how boxing is affecting a particular application. So I'm going to go ahead and share my desktop. I hope you guys can all see the desktop now. You should see a little image of a Axum Pocket PC. Okay, so after installing the Compact Framework diagnostic tools, you'll find in the Compact Framework SDK directory a number of executables. And the one we're going to start with is what we call the Remote Performance Monitor. I'm going to go ahead and start this application. And the Remote Performance Monitor is a tool that launches an application on your device and connects to it, and then starts to pull back performance data in real time from your application. So to start an application, I'm going to click this Launch button. I'll select my device, and then I'm going to pick an application and go ahead and launch it. So now the Remote Performance Monitor is connecting to my device. It's launching my application in a mode that begins sending back performance counters. So you can see as my application begins to come up, some of these counters start to change. So I'd like to start by briefly going through the set of counters that are available in this tool, just to give you a sense for the types of runtime data that we report. So starting at the top, we report just the number of exceptions thrown. I'll talk about why that's expensive later on in the presentation. As you can see, there's a large category of counters related to the garbage collector. So these are the ones that we're going to use during this demo to figure out why this particular application isn't performing the way I'd like it to. So if you scan this list, you can see things like garbage collections, which are just the number of times the collector ran, and boxed value types is the number of times that value types were boxed into reference types, and so on. Moving down, the next category is generics. And here we just show you the number of open and closed types and methods created as the application ran. So an open type is like list of T, for example, or an uninstantiated generic type. And then the example of a closed type would be list of int, for example, or a concrete instantiation of that particular type. The next category is interop. Here we talk about the number of calls that are made both through pinvoke and through com. And this complex marshalling counter is interesting in that it tells you the number of times that the compact framework marshalling layer had to do data allocations and copies as part of marshalling. So it tells you how many times some expensive marshalling operation happened. If we scroll down, we'll next see a category for the JIT. This tells you how many bytes we've JITted, how many we've thrown out under memory pressure, and so on. The loader category will tell you how many classes we've loaded, how many methods we've loaded, app domains, and assemblies. The locks and threads category of this tool is useful for a few things. First, to see how much activity is going on in the thread pool, how many threads have been created in the thread pool, how many times that threads have had to wait on each other, synchronize in order to continue. So the locks and threads category is also pretty critical to performance. The next category is memory. These are just counts in bytes of the 5 private heaps that the compact framework creates within your address space as your application is running. One interesting thing to note here is if we look at the size of the GC heap, you'll notice it's 64K. Because remember I said we allocate in 64K blocks, and apparently the startup of this application was straightforward enough that we didn't need to allocate any more than that. So the last two categories are networking and Windows forms. So the networking category just tracks the number of bytes sent and received to and from your application just at the socket level. And then WinForms tracks all of the graphics objects, windows, brushes, controls, graphics objects, those sorts of things that are created while your app runs. So far we've been looking at this data just in this tabular form in the Remote Performance Monitor, but viewing data graphically, especially when you're looking for application trends that occur over time, is much easier to do looking at the data graphically, So let's do that using just the regular standard Windows Performance Monitor. So the first thing I need to do is tell the remote performance monitor to publish all the data that it's gathering and send it to Performance Monitor. Okay, now I'm going to start Performance Monitor, and what I've done is created a few kind of preset Performance Monitor files that track various GC counters that are of interest. So this first one that we're looking at is just the number of garbage collections that happened. So now let's start to run the application. So what this application was the beginnings of a simple game that I started to write. And I didn't get very far. All I can do so far is go ahead and create a new game. And all I do is just paint these little 2D blocks across the screen. So pretty straightforward. And then I can go ahead and rotate these blocks around in a few simple ways. And if you just visually look at the application, you'll notice that the painting is pretty jerky. It's pretty slow. So, I'm thinking all I'm doing is running through this array that I have, making little 2D graphics drawing calls. So why is it that this is painting so slowly? So if you look at our remote performance monitor graph, you can see that we've already performed, I think it's 5 garbage collections. So every time I go ahead and rotate these blocks, you'll notice that that counter bumps up another time or two. So clearly I'm doing something horrible in my painting loop that's causing the garbage collector to kick in every single time that I try to do some painting. Okay, so the fact that the GC is so busy tells us that we need to look a little further. So the next thing I'm going to look at is a few more counters. These counters are the bytes collected by the garbage collector and the bytes in use after a collection is done. So one of the things that gets a little tricky with these counters, especially in the GC area, is that looking at any one particular counter really doesn't tell you all that much. We looked at the GC counter and we know that the GC is busy, but we don't know why. So what you really need to do is look for patterns and relationships between various counters. So one pattern I like to look for next is this relationship between how many bytes are collected by the GC and then how many bytes are left after the GC is done. So I'm going to go rotate my game blocks a few more times. And what we'll see is that the bytes collected by the GC, that bumped up when I did a GC. I'll do it again, and it bumped up again. But we see that the managed bytes in use after GC, which is the green line on that performance graph, stays consistent. So this is telling me that whenever I'm rotating my blocks, I'm doing something that's causing a lot of short-term or short-lived objects to be created. A lot of things that are allocated, used quickly, and then they're just garbage. They just get collected right away, as indicated by the bytes collected by GC line. So this relationship, in this case, is a red flag to me because I'm in a portion of my application where I don't expect that I'm doing anything interesting memory-wise. However, I'm seeing all this GC activity. So I do want to say, though, that viewing a relationship between these two counters like we're looking at now is not always a source of problem. A typical allocation pattern for an application is that the application runs for a while, it creates a number of objects, the collector kicks in, they get freed, so that value comes back down, and you get kind of the sawtooth pattern over time. So the key is when you see this particular pattern in a place in your application where you don't expect it. Okay, so now we know something's going on in the GC heap. Let's dig one level deeper. So my next performance monitor graph shows the relationship between all of the managed objects that are allocated, which is the yellow line, managed string objects that are allocated, which is that kind of tannish, greenish line, and then the purple line is boxed value types. So remember again, I mentioned that both string allocations and boxed value types can cause are common sources of garbage being created behind the scenes as an application is running. So I'm going to go ahead and keep rotating some blocks. And now we see that managed objects allocated jumps up, of course, and right with it goes boxed value types. In fact, if I keep rotating, you'll see that they just move perfectly in lockstep. So in this case, managed string objects allocated is doing nothing, so clearly that's not our concern. So by looking at this graph, I now know that something in my loop is causing a large amount of boxing to occur, which is causing the GC to kick in, which is causing it to collect all this data, which is slowing down my painting. So, okay, so now I know I'm boxing, but the next step is to figure out where I'm boxing. So I'm going to close out of my graphs. And I'm going to stop the application in the Remote Performance Monitor. And now we're going to jump to another tool that will allow us to dig in to the GC heap in an even greater level of detail. And this tool is the CLR Profiler for the .NET Compact Framework. So if you've done much development with the full .NET Framework, you may remember this CLR Profiler tool as the sample that shipped in the first several versions that provides a good memory profiler. So for the Orcus version of the Compact Framework, version 3.5, we've taken this application and moved it to the Compact Framework, so you can now profile device applications with it. So, and you use this in very much the same way as you would RPM. You select the device that you want to connect to in the application that you want to run. So instead of running the application and going through all the steps of rotating all those blocks again, I've just saved off a log file from a previous run that I'm going to go ahead and open. So the initial screen that the CLR Profiler shows you gives you some basic data about the memory activity in the GC heap as your application ran. So we see that we've allocated about 6 megabytes worth of data during this application run. Under garbage collection statistics, we can see that the collector ran 8 times and so on. So let's start by looking at a histogram that shows object allocations by size. And our goal here is to determine where in our application all of this boxing is occurring. So this graph on the right-hand side of the screen, you can see a legend that maps the colors of the blocks in the graph to type names and also to some data about the number and size of types, of instances of that particular type that was created. So, for example, we can clearly see that this type called box.block clearly dominates all of the allocations, that we're making. In fact, we can see that of our almost 6 megabytes, 5.5 of them are allocations of these blocks. That amounts to 97% of all allocations that we did as part of our application are done to allocate these blocks. So we now have one more piece of information. We now know which type is causing the problem. So next, let's drill in a little farther and see where these types were allocated. So I'm going to go ahead and say show who allocated. And this brings up a graph that shows method calls and allocations. So at the beginning of this graph, there's not a lot of interest. You can see we start at program main and we call application run and we go through some internal WinForm stuff, and not until we get to the end is there anything interesting related to our instances of our blocks. So here we can see that we have 5.3 megabytes of blocks allocated at the time I took this. Then we can step backwards one step and we can see that there's a method in our main form called rotate game blocks that caused 4 megabytes or 75% of those blocks to get allocated. And there's another method called initialize game blocks that caused 25% of those to get allocated. So now we know which methods within our application cause those allocations to occur. So I want to look at the data in a different way now, and this is with this timeline view. I'm going to go ahead and change the scale just so we can see it a little better. So what this view shows is the contents of the GC heap over time. So the horizontal axis is time, and the vertical axis is object addresses. So we can see the little blue ticks here indicate the various GCs that have occurred, GC4 and all the way up to GC number 8. And again, we have our color-coded legend over here that shows us that everything in red is instances of these blocks. So one thing I find particularly useful about this particular view is it allows us to look at allocation graphs based on time. So I'm going to go and select a point in time very early in the application, and I'm going to say show who allocated again. Then if I scroll over to the end, now I can see that of the blocks that have been allocated, 99% of them came from calls to initialize game blocks. However, if I look later on in the application, by selecting a point in time later and say show who allocated, now when I scroll to the end, I can see that pretty much all of the allocations made were done by calls to rotate game blocks. So you can use this to get a sense for allocations as an effect of time while your app ran. The other interesting thing here is to look at this free space. All the areas that I've now highlighted in black are free. So you can see there are likely times where compactions have occurred. Like here, for example, there's a little tick that indicates a garbage collection, after which point this block of free space is now gone. So that's an indication that we've likely compacted down. Okay, so that's the CLR profiler in a nutshell. There are endless features in this tool. We could easily do an hour demo just on this tool, but the point being that it allows you to look with a great amount of detail into the GC heap to understand where allocations are coming from and where they're coming from over time. So now we know that we have two methods that are suspect, one in particular, this rotate game blocks. So now I can go back to my application and find the place where that boxing is occurring and fix it. Okay, I'm going to go back to the slides. Okay, so quickly, what is a good way to fix this boxing issue that we looked at? As you saw in my example, I was using a generic, or I shouldn't say generic, a non-generic array list, just a simple array list to hold my objects. And in fact, that was what I was using in the application we were just looking at. So by using a more specialized type, using generics, you can avoid these typecasts that result in this boxing. So this slide has two examples. One uses the non-generic array list, and one uses a specific list of int. Then it just loops through 100,000 times, it looks like, these couple arrays adding values to the arrays. So let's look at the performance numbers. These values show the values of various counters that are reported by RPM. And as you can see, well, some of them should look familiar. Boxed value types will look familiar, bytes collected by GC, and so on. So the generic implementation is certainly much more efficient. Almost no boxing. The GC never runs, whereas the non-generic implementation caused the collector to kick in 3 times. and collected, well, boxed over 200,000 types. So that's one good way to avoid the cost of boxing. Okay, so let's move ahead now and start into the section on tips and tricks. So performance is often one of those topics, one of those features that's kind of hard to pin down as to what it really means. And I think what it really means in the end, or what it really comes down to, is perception, your end user's perception of how your application is running. So the important thing to do as a developer is to identify the scenarios that will affect your end user's experience the most, and make sure that those have targets identified for them in terms of performance, and that you have excuse me, that you have infrastructure set up to measure the performance of those scenarios. So here are a list of performance measuring tips that we use on our team. We use environment.tickCount, just before and after the block of code that you'd like to measure. It's important to start from a known state. We used to reset our devices between every application run when we were doing our perf runs. We don't do that anymore, but we at least make sure that no other processes are running, there's not a lot of network activity going on, that sort of thing. It's also important to run each test in its own process or its own app domain. And the reason for this is to kind of get to the point of measuring only what you intend to measure. If you ran multiple tests in the same app domain, you would find the Compact framework reusing some of the runtime data structures that it created from the previous run. So subsequent runs are getting an unfair advantage, so to speak, because there's less work for the Compact framework to do. So definitely destroy each app domain, or destroy the whole process and just start another process up is actually probably even better. And also remember to understand the JIT time versus the runtime costs. So if what you're measuring is some loop or some particular control flow through your application, call that flow once without measuring it, just to cause the JIT compiler to run to create the code, and then go ahead and start measuring the performance. Otherwise, you're factoring in the JIT time, which of course is the Compact framework's expense. It's not your expense. So again, you're getting a skewed performance number. So startup time is a particular pain point, I know, with .NET in general and with the Compact framework. And what we found in looking at it is that most of the time during startup is spent in the OS doing signature checks. And the measurements we've taken have found that it takes about a second per megabyte of file size to verify these signatures when an app is starting. So if you're loading a typical application that's going to use MS Core Live and WinForms and System and those sorts of things, there are checks done on those files as they load. So the good news is that as newer versions of the Compact framework find their way into ROM on Windows mobile devices, the performance cost gets much better, because when a file is in ROM, we assume that it's trusted and none of these checks occur. So when the Compact framework is installed in ROM, you'll see a much better startup performance trend than you will when it's installed in RAM. So the guidance here is to keep your primary executable small so that it loads quickly. Don't use a strong name, at least for the primary executable. There's no real need to, and it saves some signature checking time. And we've seen people do all sorts of things to address users' perception, like a small executable that loads a splash screen and those sorts of things. Okay, so I'm going to start moving quickly here in the interest of time. User interface, the primary thing to remember in Windows is that all user interface work is done on one thread. So when you have event handlers that are connected to buttons and menus and whatever, the code that executes in your event handler is running on the UI thread. So anything you do to block the application or to take a lot of time in those event handlers will stop the UI from interacting. And that's certainly a way to give a poor perception to your end users. So keep your event handling code tight and do as little work in there as possible. If there's a lot of work to do, farm it out to background threads and wait for it to come back. But don't block in your UI event handlers. Collections can also be interesting from a performance perspective. They often occur in performance-sensitive areas, lots of looping, over large sets of data, those sorts of things. There are many options. We've seen the old non-generic collections like ArrayList, the newer collection types that use generics. You can also write your own custom collection types. Generally, a strongly typed collection will give you better performance than a loosely typed collection, primarily because you can avoid much of the boxing cost. If you're using an existing built-in collection, try to pre-size it appropriately. Many of the collections in the .NET framework come with some preset size, and then if you go over that size, it allocates a whole new collection of a bigger size and then copies all the data from the old collection to the new collection. So that's another case where you're creating all sorts of garbage that you probably wouldn't have to. If you're storing custom types in your collections, your own types, be sure to override get hash code and equals. Those are called a lot for comparisons and searching and sorting and those sorts of things in collections. And the default ones, I believe, use reflection to determine the shape of your type, which can be expensive. So keep your implementations of get hash code and equals fast and efficient, and definitely remember to override them. I'll say a word about reflection here. I mentioned it as an expensive operation. There's both a performance cost and a working set cost to reflection. The working set cost is just related to the amount of data that the runtime creates to represent each class and each member of an object. So if you have an application that loops through all the types and assemblies and loads all of them, you can think along the order of, we create a data structure that's about 100 bytes in size for every type and about 80 bytes in size for every method. And furthermore, this is the data that I was referring to earlier in the presentation that we never throw away and that the garbage collector doesn't see. So the more of this kind of iterative reflection work you're doing, the more runtime data you're building up, the more memory pressure you're putting on the system, and there's currently no way to get rid of it. Invoking methods through reflection is also slower. Think, 10 to 100 times slower. And again, just because of the, processing we do at runtime to construct all the right structures to send the call to the right place and pass the parameters and so on. Reflection is used behind the scenes in a few cases. So just as boxing and string manipulations occurred maybe when you didn't expect it, reflection can as well. If you're using web services, when we generate proxy code, we use reflection. With serializers, we reflect over the type when we're creating the serializer. So in these cases, be sure to cause these operations to happen once and then persist or keep these objects around and reuse them, just so that we're not going back to the costly reflection-oriented operations again each time. So, okay, I'm going to end with a quick word about interop. I mentioned mentioned earlier that pinvoke is more expensive, and this is just the cost of constructing the runtime data we need to do to jump to the native side and then to call back. So the guidance here is similar to the old guidance you used to hear with COM, all the time before, and that's make a smaller number of calls with a larger number of data will be more efficient than a large number of calls with a small amount of data, just again because of the cost of crossing the boundary. And then watch out also for these cases of what we call complex marshalling. So if you're marshalling a type like an int or a Boolean or something that has an identical representation on the native side as on the managed side, then there's really no work to do to marshal. It's just either a straight copy or even just a pointer reference. But if you're using some of the more complicated types, like some of the COM types like variants and strings and so on, then we need to do allocations and data copies to translate between, say a C array and a safe array, for example, in which case your performance can be affected. So track this with the performance complex marshalling performance counter in RPM. Okay, so we're at the end of our hour. You noticed I skipped pretty quickly through the stuff at the bottom half of the slide deck. It was a lot of information, probably may not stick in right away, and I even skipped a few things you may have noticed in the interest of time. But the slide deck is there. There are references at the end of the deck that will point you to more information about those tips and tricks. And as always, feel free to ask questions on the Compact Framework Msdn form. Our product team monitors that very closely. We have people assigned on a rotating basis to make sure that every question gets answered and addressed. So if you have questions about some of the stuff I zipped quickly through, just please ask. So in summary, remember to treat performance as an application feature, just as you do any other end user feature. Understand the scenarios that will affect your end user's perception of performance and make sure those are tuned well. The best way to do that tuning is both through, knowledge and tools. If you have the knowledge of how things work internally within the Compact framework, primarily memory management and some reflection and jitting sorts of issues, and couple that with the diagnostic tools that we went through, that should give you a pretty good sense for what's happening behind the scenes in your application. Okay, here's the resource slide I mentioned. And Tracy, I guess it's back to you for survey.
Excellent. Thanks, Stephen.
Yep, sorry.
I do want to remind everybody that for more information, they can print a PDF of today's session. To do that, just go to the File menu in your upper navigation bar. Also, now's a good time to submit your questions into the Q&A panel. Please type them in and hit that Ask button. We will be getting to those in here in just a moment. Also, I'm going to be posting a survey here. If you'd all please take a minute to fill that out before you log off. We do appreciate your feedback. As a reminder for upcoming and previously recorded webcasts, you can visit Microsoft.com/webcast. You can go here to access this webcast, which will be available for download in about 24 hours. If you have any webcast content ideas, something out there you'd like to see and you haven't yet, we'd love to hear from you. Take note of this link here. And for anybody who's interested in receiving a free 14-day trial of Microsoft Office Live Meeting, you'll want to visit Microsoft.com/presentlive. And here's the survey from our session today. Please follow the links provided to complete today's webcast evaluation. And Stephen, it does look like you have some questions waiting there for you.
Oh, okay. Okay, the question is, why is there no reference exception when connecting to a device with the RPM app on some PCs and not others? Well, a few, I guess I should, Tracy, do I explain or do I type or do I do both, or what's the best way?
Go ahead and just answer it aloud.
Okay, and then just type the answer or not?
You don't need to type it right now.
Okay.
Yep, that's fine.
Okay, so there are a few things with RPM to remember. If you're using the version of RPM that comes with the version 2 family of Compact Framework products, version 2 SP1 and SP2, there are some manual deployment steps that you have to that you have to take in order to get it to work. They're posted on a blog site. I'm going to type that in here, blogs.msdn.com/StephenPR. If you search for RPM, it'll tell you that there are 3 or 4 DLLs that you have to manually copy down to the device. If you're running the version of RPM that comes with Orcus, with version 3.5, then you don't have that issue. So then I guess I wouldn't expect a null reference exception in particular. So I think if you have a specific case where you have that problem, just email me with the version of RPM you're using and an example, and we'll try to figure out what's going on. So my email is StephenPR, STEVENPR, @Microsoft.com. Okay, so I just say post to all.
That's perfect.
Okay, so the next question is about the CLR profiler and string builder and strings. So what are the issues associated with compacting GC pools? Well, I guess only, so from the application's perspective, from the application developer's perspective, there should be no issues or no impact with compacting the GC pools. It's just a technique we use to enhance performance. So, over time we build up these numerous 64K segments, and as we collect, there can get to be large holes in those segments. So in order to reduce the number of segments that we have to look through, then we just compact all the data down into a fewer number of segments, so it's quicker to look through. And then also it gives us a chance to return memory back to the operating system, so there's more physical memory available on the device. The second question is, why is all UI manipulation forced to use a single thread? So, boy, I don't even know if I can answer that. That is kind of a long-standing thing in system windows.forms. And I guess I probably technically don't know why all UI manipulation has to work on a single thread. Maybe it is that some of the underlying stuff isn't thread safe, or I honestly don't know. I can certainly find out if you want more information. And the next question, can we use regular expressions in NetCF? Yes, we do have the system.regularExpression class. Okay, next. I did not hear where all the tools for NetCF 3.5 came from. I looked for NetCF trace on my machine and did not find anything. Ditto for a Google search. Okay, so with this question, the directory that I was showing you on my device was just an internal build off of my development machine. So it had all sorts of internal stuff that we just use here as we develop, and that's what that NetCF trace thing was for. I'm not even sure, honestly, what it does. I haven't used it, or I don't know, honestly, if we intend to ship it as part of the Orcus tools when they ship. But anyway, that's why you saw that tool that you won't find on in the regular Compact Framework SDK. Okay, next question. What is a strong name? So a strong name is the techniques in .NET that you use to uniquely identify an assembly. So what it involves is a digital signature over your assembly created with a public and private key pair. So what that does is two things. It ensures that your binary hasn't been tampered with or hasn't been altered from the time you signed it until the time we run it. And then it also is a way that you can guarantee that assemblies that you are linking to come from the publisher that you expect they're coming from. A strong name isn't an authenticode signature in the sense that it doesn't imply a trust relationship between certificates, or in fact it's not certificate-based at all. It's just a technique for identity in .NET. And the reason it can be expensive is because of the time spent verifying the signature. Next question, do you support using custom exceptions or use error codes to propagate the business errors in layers? Well, we support both. You can certainly use custom exceptions or use an error code. In general, if we're talking about performance, an error code is going to be much faster. Exceptions, however, are probably much more in line with the .NET programming model, if I should say that. I would say that if you're truly reporting exceptional conditions, things that you did not expect to happen, then I think exceptions are the way to go. I think that's just an easier programming technique, but you can certainly use either. Next question, any good diagnostic tools for CF10 apps? Well, yes and no. So you can use all of the tools that we use today for CF10 apps. Both versions 2 of the Compact Framework and version 3.5 of the Compact Framework will run CF10 apps unchanged. So what you would need to do is run your CF10 app using either version 2 or version 3.5 and then use the diagnostic tools. You don't have to rebuild it or recompile it or anything. You can just take your existing binary and run it directly. But you will have to be using one of those newer versions to use the tools. But the applications run pretty much the same. So that should give you a pretty good idea of how your 1.0 app is behaving. Next question, on my slide about using generics, is there a way to get the slide without the performance data on it? That particular slide is one of those it's one of those build slides that starts without the performance data, and you click on it and it shows the performance data. So I guess when you get PDF, it probably has the performance data already sent over the top of it. I guess, Tracy, can you get just a regular PPT file, or?
Yes, they'll be able to access the PowerPoint slides. Tomorrow they will all be getting an email with information about how to download the actual PowerPoint deck. So,
okay.
Yep, they'll be able to get their hands on it.
Okay, so that's the easiest way then, I guess, is just to get that deck and just cut out those little green boxes that had the performance slides on them. So, okay, so that's all of the, oh, no, there's another one. Is typecasting expensive or object.toString expensive? So the typecasting is not expensive if you're casting just from a reference type to a reference type, and there's kind of almost no work for us to do. It is expensive if you cast from a value type to the reference type. That was the boxing example we saw. Is object.toString expensive? And that depends on the object. The default implementation of toString does use reflection to get the name of the underlying type, which is what it prints out. So if you're using toString a lot on types of your own, it's definitely recommended that you override object toString and just return, a string literal. So toString can be expensive, but so override it if you have a performance-sensitive case. Next, don't all PowerPoints require a password to edit? I don't know, Tracy, what's the answer to that one?
The PowerPoints to have a password, yes, they are only downloadable that you're not able to make changes to them.
Oh, okay. So maybe then I should just...
If you want to...
Or should I make this other slide available?
Do you have a blog you can post it to?
Mm-hmm.
Go ahead and post it to your blog. Looks like they have your blog address down at the bottom in the Q&A panel.
Yeah, okay.
They can take a peek at that if you just want to post that one slide for them to use.
Okay, I'll do that. Okay, I see another one. Or string s equals object toString. Well, I guess that's just the same as, toString is, or can be expensive for types where where the implementation hasn't been overridden. So now the question disappeared. Okay, so Tracy, do you want me to go back and type these answers to save them for some sort of a transcript or something, or?
Nope, I think looks like we should be good.
Work? Okay.
All right, well, with that, I do want to extend a very special thank you to you, Stephen, for your presentation today and answering all the great questions we had come through the queue. Well, ladies and gentlemen, this is going to conclude today's session. Thanks for joining us. You may now disconnect from the audio portion of today's presentation.